Welcome to the very first episode of Cracking the Data Science Interview Series. I'm thrilled to embark on this journey with you, where we'll unravel the mysteries of data science and machine learning interviews and equip you with the skills needed to ace them. Whether you're aiming for that dream job at a top tech company or simply want to sharpen your data science prowess, you're in the right place. In this series, we will dive headfirst into the realm of data-driven problem solving and career preparation. Each week, you can expect a fresh batch of insights, strategies, and solutions tailored specifically for conquering your next data science or machine learning interview. Today, we're kicking things off by tackling not one, not two, but three popular data science and machine learning interview questions. We'll dissect each question, unraveling what the interviewer really wants to know, and provide you with detailed solutions that will leave your interviewers impressed. Without further ado, let's jump right into our first question, shall we? Alright, our first challenge is a classic, implementing the binary search algorithm. Now, if you're not familiar with it, it's okay. We'll walk through it step by step in this video. Here's the breakdown. We start with a sorted array and a target value we want to find. We initialize two pointers, low and high, to the start and end of the array respectively. Then, we enter a loop where we calculate the middle index and compare the value at that index with our target. Depending on the comparison, we adjust our pointers accordingly until we find the target or exhaust the search space. As you can see, the binary search function returned 2, which is the index position of the target number 16. And there you have it, a sleek, efficient binary search algorithm ready to tackle any sorted array. Now let's move on to our second question. Next up is the bias variance trade-off, a fundamental concept in machine learning that often leaves interviewees scratching their heads. But fear not, for we are about to demystify it. At its core, the bias variance trade-off encapsulates the delicate balancing act between bias and variance in our models. Imagine a seesaw. On one end, we have bias, representing the assumptions our model makes about the data. On the other end, we have variance, reflecting the model's sensitivity to fluctuations in the training data. But why does this trade-off matter, you ask? Well, let me tell you. High bias can lead to underfitting, where our model fails to capture the complexity of the data. On the flip side, high variance can result in overfitting, where our model memorizes the training data but fails to generalize to new, unseen data. Striking the perfect balance between bias and variance is crucial for building models that generalize well to unseen data. Last but not the least, we have a hands-on question, performing dimensionality reduction using principal component analysis, or PCA for short. Here's the gist. PCA allows us to reduce the dimensionality of our feature space while preserving as much of the variance as possible. In this snippet, we are using scikit-learn's PCA module to transform our original feature matrix X into a new matrix X PCA with just two principal components. Dimensionality reduction not only speeds up computation, but also helps uncover underlying patterns in our data, making it a powerful tool in any data scientist's arsenal. Now, before we wrap up, let's take a moment to appreciate the power of principal component analysis, or PCA. This versatile technique not only reduces the dimensionality of our feature space, but also uncovers hidden patterns lurking within our data. By transforming our original feature matrix into a new set of orthogonal axes called principal components, PCA enables us to focus on the most significant sources of variation in our data. This not only simplifies our analysis, but also enhances interpretability, a crucial aspect when communicating our findings to stakeholders. So whether you're dealing with high-dimensional data or seeking to visualize complex relationships, PCA has got your back. Incorporating PCA into your data science toolkit opens up a world of possibilities, from dimensionality reduction to feature engineering and beyond. And the best part, it's incredibly easy to implement, as demonstrated in our code snippet earlier. With just a few lines of code, you can harness the full potential of PCA and unlock deeper insights from your data. So next time you're faced with a mountain of features or struggling to make sense of your data, remember the power of principal component analysis. Dive in, experiment, and let PCA guide you to a clearer, more nuanced understanding of your data. And there you have it. 3 top-notch data science and machine learning interview questions, dissected and conquered. I hope you found this inaugural episode insightful and empowering, but wait, the learning does not stop here. For an in-depth recap of today's episode, be sure to check out the accompanying blog post linked in the description below. Dive deeper into the concepts we covered and access additional resources to turbocharge your data science journey. And hey, if you want to get hands-on with the code snippets showcased in this video, head over to a Google Colab notebook. Experiment, tweak, and explore the magic of data science firsthand. Remember, your feedback fuels our growth and helps us tailor future episodes to your needs. So if you enjoyed this video and want to see more content like this, don't forget to hit that like button, drop a comment with your thoughts, and subscribe to join our growing community of data enthusiasts. Until next time, happy coding and thank you for watching.